Cool, yeah. I think it's almost time. So, hi, my name's Tom Westerhout. I'm going to be chairing this session. I've been a happy Chapel user for a couple of years now. And as the first talk of the session, we'll have Brad Chamberlain talk about the computer language benchmarks game and Chapel 2.0. Um, and I think, Brad, you can take it away.
Okay, great. Thanks very much for the introduction. Yeah, this is going to be kind of a lightning quick talk about the computer language benchmarks game in Chapel 2.0. This is one of my hobbies on the project. I do this in the evenings and weekends sometimes when I'm done working. That's my confession. So if you're not familiar with the computer language benchmarks game, this is a website that compares a few dozen languages using 10 reasonably simple benchmarks. This is a snapshot of the front page of the game, and I'll show you other snapshots as we sort through and look at some of the results here. Each of these benchmarks exercises some useful things like floating point performance, or I/O, or vectorization, or big ints, memory utilization, things like that. And so you can often find a benchmark that has idioms and patterns you care about, and see kind of how do different languages do with that. You can compare the benchmarks in terms of a number of features. Wall clock time, code compactness are the two that we tend to care about the most. And the site really encourages people to browse the source code and not just look at the speed, but like, well, how much effort and pain did it take to do that? But that obviously requires a large amount of effort. So we often use code compactness as a stand-in for that. The game is also open, so you can submit new code submissions in the languages that it supports, as long as you follow the same algorithm as other entries. You can't be sort of totally creative in terms of algorithmic approach. Our philosophy about the computer language benchmark game is to submit versions that are fast but also very clear. And sort of a goal we always try to keep in mind is to create versions that if you were learning one of these benchmarks for the first time, you would think like, oh, I'll look at the Chapel version. That'll be a really easy way to learn it. That's sort of what we're always striving for. We then use the results on the game to understand where we fall short. Where are we not keeping up with the other languages in terms of performance? Or where do we maybe not have the expressiveness or the capabilities that some of these other languages do? As you surf through the site, you can find your way to one page like this for each of the 10 benchmarks. This is the spectral norm benchmark, and this shows the results for it. And I'm going to teach you a little bit about how to surf these results. First of all, to learn what the benchmark does, you can click on this description here. That'll give you a short description of what the benchmark does and what it's computing. A little bit further down here, we see a few entries pulled out. These are sort of exemplary versions that are particularly simple and clear. So, good ones to learn from is the way I think about it. And we're always happy when Chapel shows up in this list, which it does in a few cases. Then further down here, we have sort of the main pack of results, kind of the leading contenders, if you will. So let's look at how these results are displayed. By default, this is sorted by seconds, which is wall clock time. You can see here's the fastest Chapel version here, Chapel number 2. It took 0.73 seconds to run. The very fastest is 0.72 in Rust. So you can see that we're within 1.0 of the baseline here, that Rust version. And this column here is basically how far off is each version from that baseline version. You can then click on these headings to sort by other things, like this GZ is the code compactness or code size metric. So if I click on that, we'll resort the entries by that. You can see our Chapel number 2 entry. Well, what do my comments say? We can see a Chapel version here that's 1.1 times as, now we're measuring compactness. It's 1.1 times bigger, if you will, than the baseline Ruby version. And then that Chapel number 2 version that we were looking at before is even a little bit bigger, 1.2 times. So this shows kind of the typical tension between our faster version being a little bit more code and our more compact version presumably being a little bit slower. If we scroll down to the bottom of this list, we see a separate section down here that's called the handwritten unsafe versions. I call these the heroic versions for brevity. And these can outperform the baseline we're comparing against. See, like you can see this C version here is actually twice as fast as the baseline. So it has this factor of 0.5 here. If I scroll back up, we can find, here's that other Chapel version that I saw. I'm sorting by time again here. And you can see that it is about twice as slow as the baseline. So even though it was more compact, it is a bit slower. So in Chapel, we can see here we've got this version that's 2 times slower and 1.1 times less compact, and this other version that's about as fast as the baseline, but slightly less compact, slightly more code. So this sort of tension is something we're very interested in Chapel, And so what we like to do with these results is plot these as a scatter plot. So here what I've got is a scatter plot in which this vertical axis is the execution time normalized to the baseline. And the other axis is the code compactness measured with respect to the baseline. And here I've plotted all of our fastest and most compact chapel entries. And we can look for the two spots corresponding to those spectral norm versions I was showing you. So here's the one that was 1.2 the code size, but equal in speed. And here's the one that was twice as slow, but 1.1 the code size, right? And we can go through all of these and sort of label which benchmarks are each of these, which is the most compact, which is the fastest. Sometimes they're one and the same, and get a sense of where chapel entries live in this space relative to the other entries. And then we can take the geometric means, and these halos here are the standard deviations of those fastest entries to kind of get a summary, essentially, of here's sort of, if you take all of our most compact programs, where they fall, and here's where our fastest programs all fall. We can then take those geometric means and repeat this process for each of the languages to kind of come up with a map for where do the languages fall in this code compactness versus speed space. And so you can see the scripting languages, as you might expect, are the most compact. They're the furthest over here on the left, but they're quite slow. And then down here at the bottom, we've got a bunch of fast languages that if I zoom in will resolve themselves. Rust, C++, C#, and C. And Chapel and Julia are sort of uniquely kind of down to the left here. So fast, reasonably fast, but also reasonably compact. So sort of a sweet spot between scripting and traditional low-level languages. Now these entries include the heroic versions. If we go through and remove those heroic versions from this normalization, we see a slightly different landscape. Chapel edges further ahead of Julia here and gets closer to, well, it's ahead of Fortran, closer to C++, and getting closer to C and Rust. So that's kind of intriguing. Like if you're not willing to be heroic, maybe Chapel's not as far behind as it may have looked in the previous graph. Let me skip past this slide in the interest of time. I just want to brag here. We were really excited when 2.0 came out. I mentioned this in my intro talk today, that without any code changes to our n-body version, it became both the fastest and the most compact if we sort by speed or code size. And since I've been following the competition, that's the first time I've been aware of a single code being both the fastest and the most compact. So that's definitely a point of pride for us. And another case where we're happy it's up here in the sort of exemplar section. All right. As you know, we did Chapel 2.0 recently. We stabilized a bunch of language and library features. We broke a bunch of code on the way, and that includes a lot of our codes that were submitted to this site. So this is a table that shows updates we had to make to the code since last year in order to get them working with Chapel 2.0. And I think this is sort of indicative of some of the pain users have been feeling over the years, but will cease to now that we've got 2.0 out. There are still a few unstable features that we rely upon. That's unfortunate. It'd be nice if we were only using stable features for these benchmarks, and I've called those out here. This is my last slide. I just want to say there are opportunities for future improvement here. This binary trees version you can see is a huge outlier in terms of speed. That's because we don't have any sort of memory arena or object pool concept. Most of the fastest versions do, so we're much slower than them. We've already got some improvements for regex going in. That should be live in 2.0. But there's probably more we could do here with a better regular expressions library. These revcomp and k-nucleotide benchmarks are sort of further off and to the right here than we'd like. And there are also opportunities for style improvements here. I'll mention that this can be a very addictive way to spend your time. So if this is intriguing to you, proceed with caution, but we'd love to have other people working on this as well. And I'll stop there to see if there's any question with my last minute or two.
Well, thank you, Brad. Let's see. Yeah, so there was a question from Oliver
Okay.
about the binary trees, but it seems that you've already answered it.
He was wondering why is it way up here?
Yeah, indeed.
Yeah, so our version of this is very clean. This is basically allocating a bunch of tree nodes and then freeing them in various patterns. And we have a very clean implementation, but it's literally doing an object by object freeing, whereas many of the others basically can allocate and then free all in one fell swoop. And I think that is the main thing that causes this big lag here.
Do we have any other questions? No, then I'll ask a quick one.
Okay.
Have there been any experiments with like heroic versions in Chapel? Is there a way to get it to kind of perform on the same scale?
That's a good question. I would say we've mostly tried to shy away from that because we don't want to, we're trying to avoid at least the entries that our team submits, having entries that fall way out here. But there's this one case you can see off that's off this side of my graph here. There was some point at which these new RevComp versions started showing up in Rust, C, C++, I think. And they were like, just blew everybody else out of the water and kind of messed up our geometric means to a point that we were really embarrassed about them. So we actually ported those versions. They are much prettier than the Rust C, C++ versions, but they're very low-level parallel synchronous, or lots of synchronization kinds of implementations. So that's probably the best example we have today of having done something quite heroic.
Got it. Yeah. Thanks.
But more could be done there for sure. Yeah.